All right, guys, let's finish section 8.2, part 1. I know it's a little annoying with the A and B, but it is so much easier to download. So we might just have to stick with this for a while. We'll see how it goes. All right. Oh, dear. Okay, sorry about that. Okay, so I'm going to try to number my examples too, because this would be like example 6. Okay, we're starting in the middle. That's why it's part B. All right, so we've got a few more examples to go through. We're determining whether the series is convergent or divergent. And if it's convergent, we actually have to find the sum. If we add them all together, what does the sum turn out to be? Okay, so here's another example. They just changed the letter on us. You are more than welcome, like if it's annoying enough to change the letters, if we want to just go back to N, we can. I probably will. -1. There's enough to think about that sometimes it makes a big difference if we just look at it in terms of N. All right, so now we got to decide what are we going to use. Is this geometric? Remember, geometric is when we have r to the n power. So this has nothing to do with geometric. So I think I'm going to do test for divergence, okay? Because remember, this is kind of something we've seen before. In the test for divergence, we actually take this rule, and we don't worry about that it's being a sum. And we just do the limit as n approaches infinity of n minus 1 over 3n minus 1. Okay, and I think that I think this is very similar to example 5, but maybe it was a good transition. So if we do infinity, if we plug in bigger numbers, we go to infinity. If we plug in bigger numbers here, we go to infinity. So we can do L'Hopital's rule. Remember, this is going to be important that you kind of write down what you're doing and what you're thinking. All right, so if we take L'Hopital's rule, we take the derivative of the top, which just goes to 1, and the derivative of the bottom is 3. Okay, so remember the limit. So the limit is actually 1/3. If it doesn't equal 0, it diverges. Okay, if it does equal 0, we're back to the drawing book. We have no idea what's going on. But if it doesn't equal 0, then it diverges. Okay. All right, let's take a look at example 7. It's kind of nice just to start at the beginning here, or at the top of the page. Example 7, we're going to do the summation from 1 to infinity of 1 plus 3 to the n over 2 to the n. What am I saying here, guys? The exponent is n, so I am thinking geometric. When the exponent is n, I am thinking geometric. Okay, but we got to get a lot of things set up here. So the first thing we're going to do is we're going to split this up. I'm going to write this as 1 over 2 to the n, and then 3 to the n over 2 to the n. Okay. How come I'm thinking geometric? Because my exponent is the variable. My exponent is n. Now, this one I can write it like this: 3 over 2 to the n. This one I can get by with it because it's a 1. So remember, because it's a 1, it is okay to also do 1/2 to the n. Okay, and I'm going to do each one separate. But we have a little bit of a problem. So I'm going to remember, we also talked about we can do each one separate if we're adding. So I'm going to look at this, and then I'm going to look at this one. Let's see, 3/2. Okay, but we have a little bit of a problem. We definitely now can clearly see both of these are geometric, so we're in really good shape. But if this is a 1, this has to say n minus 1. Okay. So that's a hard one, or it's hard enough to know it's geometric. Then we got to do this. So we have to do this as, I can't change that, so I can change this, pull out a 1/2, and then I can write it as n minus 1. Okay, same thing here. This one, I have to pull out the 3/2, and then I can write it as n minus 1. So that's kind of annoying. You really have to look, are you starting at 1 or are you starting at 0? And then you have to adjust the exponents accordingly. But we are definitely geometric, so we're in good shape. Okay, so this one here, this is A and this is R. If the absolute value of R is less than 1, it converges. Okay. What about this one though? This one here, this is my A, this is my R. The absolute value of R, okay, this was 1/2, so I was in good shape. Here I'm talking about 3/2. If it's greater than or equal to 1, what happens? This is my R, greater than or equal to 1, it diverges. Okay. So I don't even have to worry. If part of it diverges, the whole thing diverges. Okay, because part of it diverged, the whole thing diverges. All right, let's try a similar one. This almost looks the same. It's a little bit different. Example 8. Okay, summation n equals 1 to infinity. I am doing 1 plus 2 to the n over 3 to the n. So same thing. I am thinking, and part of it, I like to do a bunch of examples just because we have to talk about what are we going to use. Because n is our exponent, we're thinking geometric. Okay. We're thinking geometric. Let's kind of get it set up. 1 over 3 to the n plus 2 to the n over 3 to the n. And as you start to split it up, you see it even more. Right? We can do this separately. N equals 1 to infinity. I'm going to write this as 1/3 to the n. Because that's a 1, I get away with doing that. This one, they both have it, so I'm in good shape. N equals 1 to infinity, 2/3 to the n. Okay. But this is 1, so this has to say n minus 1. Same thing, this is 1, this has to say n minus 1. So I got to pull one out. 1/3, now I can write it as 1/3 n minus 1. Okay, same thing here. Because I'm starting at 1, this needs to say n minus 1, so I pull a 2/3 out, and now I can write it as 2/3 n minus 1. Okay. Okay, so now this is definitely geometric. This is my A, and this is my R. Okay, maybe even do both. This is my A, this is my R. Remember, my R, the absolute value of R has to be less than 1, and they both are. Okay, so because they are both less than 1, they both converge. So now I can actually, this is how this one is different. I need to figure them both out. So this one's 1/3, so it converges. This one's 2/3, so it converges. So I need to do A over 1 minus R. Okay, so A is 1/3. 1 minus R, which is also 1/3. Okay, and then this here plus, and then I'm going to do it all over again. A, which is 2/3, and then 1 minus R, which is 2/3. Okay, and then I just want to work that out. This would be what? This would be 3 over 3, so this would be 2/3. So multiply by the reciprocal. So I get 1, those cancel, so I get 1/2. Okay, this would be like 3 over 3. So I could subtract, right? So that gives me 2/3 divided by 1/3. Or multiply by the reciprocal, the 3's cancel, so plus 2. So 2.5, we could also write that as 5/2. Okay. All right, so, and let's write it converges. We knew that way up here, right? But either, wherever you write it, that's fine. This converges. So on here, I want to show, you want to show me that you use geometric, that it converges, and what does it converge to? When you plug in a 1, plug in a 2, plug in a 3, all the way to infinity, and you add them together, it's going to approach 5/2. That's crazy. All right, we've got 1, 2, 3, 4 more examples. Okay, let's keep cruising. We're doing really good. All right. This one is a tricky one. X to the 9th, summation n equals 1 to infinity, the nth root of 2. Okay. The reason this is tricky, okay, let's talk about how can we rewrite this, right? If this was a 2, or we're talking about a square root, it would be to the 1/2. If this is a 3, we would write it as 2 to the 1/3. So we can rewrite this as 2 to the 1 over n. Now, let's make sure, get that okay. So those two are saying the same thing. Now, usually when n is an exponent, we're thinking geometric. But because it's 1 over n, that changes everything. That would be like, you know, n to the -1 or something. And the only way to use geometric is you have to have a regular n or a regular n minus 1. You have to, that's the only way to use geometric. So this one's a little tricky. Even though my n is the exponent, it's not a regular n, so I am not going to use geometric. It just doesn't fit that pattern. It's close. It's probably the closest you're going to get without it actually being geometric. So this one's a little bit harder. So this one we're going to do test for divergence. That's all we have right now. Okay. So test for divergence says I can actually look at just this rule. I can take the limit as n goes to infinity of 2 to the 1 over, oops, why did I make that an 8? I don't know. To the 1 over n. Should I rewrite that? The limit as n approaches infinity of 2 to the 1 over n. Oh, I know. I was going to say, the reason I wrote 8 is because I was thinking this is like what we did in section 8.1. Okay, we actually change it from a series to a sequence. Okay. And then this one, we can actually just evaluate it. What happens as the bottom gets bigger and bigger and bigger? As the bottom gets bigger and bigger, this overall fraction is headed towards 0. So it's really 2 to the 0, which is 1. Okay. Now remember, test for divergence says if I get anything, if it doesn't equal 0, if it doesn't equal 0, it diverges. That's the other thing. We're used to boxing this off and saying this is our answer. No, 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 no. We're doing the test for divergence, which means I have to look at this and make a decision. This is not my answer. 1 is not my answer. Test for divergence says if it doesn't equal 0, then it diverges. Okay, so really remember, we kind of go back and forth. We go series, sequence, and then back to series to evaluate it. Okay. That's kind of our thought process. But overall, because we're doing a series, we have to actually evaluate this, decide what's going on, and then show that it diverges. Okay. All right. 3 more. Let's try this next one. Example 10. Okay. Summation of n equals 1 to infinity. We're doing 0.8 to the n minus 1 minus 0.3 to the n. Okay. All right, sorry, let's turn. All right, what are we thinking? These are regular n's as exponents. We're thinking geometric. Okay, so this is back to geometric. So it's kind of good to do 9 versus 10. Okay, we're going to split them up. N equals 1 to infinity, 0.8, and this is 0.3. Did I say that? 0.8 to the n minus 1, and then minus n equals 1 to infinity, 0.3 to the n. Okay, so one of these is good to go and one isn't. When it equals 1, n minus 1 is beautiful. This is great. So what is my a? My a is 1. I was going to write it in red, but I just already wrote it, so skip that, right? And my r is 0.8. So my a is 1, my r is 0.8. Here, this is no good. So I got to pull a 0.3 out, and now I have 0.3 to the n minus 1. Okay. So that was a good comparison too, to kind of reference ourselves, remember the difference between the two. So here my A is 0.3 and my R is 0.3 as well. Notice both of my R's, remember the absolute value of R has to be less than 1, then they converge. So both of these are going to converge. Okay, so now it's just a matter of what does it converge to? A over 1 minus R. So now we got to go at it. My A is 1, and then I have 1 minus 0.8. And then minus, notice this one is a minus. And then I have to do A, which is a 0.3, and then 1 minus R, which just happens to be 0.3 as well. Okay. So now we just go at it. This is 1 over 0.2. What is 1 over 0.2? That is actually 5. It should actually be 5. This gives us what? 0.3 over 0.7. Again, if you just use a calculator, that's okay. So this actually, wait a minute. Let's see. Oh, I lied. This is not right. Actually, that should have been okay, right? So I do 1, what am I doing? 1 minus 0.3 is 0.7. Yeah, that is okay. So I have okay, yeah, I'm okay. I don't know. I'm losing my mind. 0.3 over 0.7, which I think is what I had. Who knows? I don't know. And then, so this changes, you know, now this would be 3 over 7, which is fine. That's what it equals. And then 5 minus 3/7 takes us to 32/7. Okay, so it definitely converges. We knew that up here, right? As soon as my R's were both less than 1, absolute value less than 1, it converges. Okay, and then we just worked it out. This one converges to the 5, and this one converges, if I can do the math right, to 3/7. And then we subtract them together to take us to 32/7. What does this mean? If I plug in 1, if I plug in 2, if I plug in 3, and I add them together, it's going to approach, even if I go to infinity, it's going to approach 32/7. All right, we got 2 more. Example 11, how are we doing on time? Beautiful. Okay, this one just looks weird. They tried to make it a little bit harder for us. They changed it to K, and it's cosine of 1 to the K. I hate how it zooms in and out. I don't get that. Okay, if we want to change it to N, we can. If we don't want to, that's okay. Don't let that scare you at all. The other thing is, notice my variable is an exponent. I'm thinking, what are you thinking when your variable is a regular old n or n minus 1? Geometric. Okay, geometric. Okay, now we got to get this looking geometric. This is just a number. In fact, what is cosine of 1? Cosine, you can just type it into your calculator. Cosine of 1, make sure you're in radians, and it should be something like 0.54. So you can even put 0.54 there if you want, if that helps you at all. You can kind of do it together if you want. Cosine of 1 is just a number. As soon as I write it like that, if that helps you see that it's geometric, all the better. Okay. The only issue is, though, this is 1 and this is n, and we need n minus 1. If this was 0, we'd be in good shape. Who wrote this problem, right? All right, so how do we fix it? We're going to pull this out. So we're going to write cosine of 1, or you can do 0.54 if you want. And then we have cosine of 1 to the n minus 1. Okay, but we're definitely geometric. This is my A, and this is my R. And this, though it looks crazy, this remembers 0.54, so my R is less than 1, so it converges. Okay. So what does it converge to? A over 1 minus R. A is cosine of 1, and R is cosine of 1. Okay. And we actually just leave it like that. That is by far the best answer, even though it looks a little messy. That's it. That's what it's going to converge to. If we plug in a 1, and then we plug in a 2, and we plug in a 3 and a 4, and we add it all, and we added them all together, this is what it would approach. Okay. All right, last one. I don't know. I think they wanted to make it harder on us. Last one, every once in a while, we're going to have to write the rule. So they give us this, 1/3 plus 1/6 plus 1/9 plus 1/12 plus 1/15 plus ... Okay, so in this last one, we're going to have to write the rule. So remember, we relate it to a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. We don't want to relate it this way, we want to relate it this way. So 1 to 3, 2 to 6, 3 to 9, 4 to 12, 5 to 15. How are we going to go from 5 to 15? It's got to be the same way we go from 4 to 12, 3 to 9, 2 to 6. So hopefully we can see, and it's a plus, so the first thing we're going to do is a summation. We're starting at 1, and we're going to infinity. Okay, and then notice the top is always 1, so 1 over, and what's the relation? How do I get from 2 to 6, 3 to 9, 4 to 12? This here might help a little bit. It's going to be what? I have to take 3 times n. Okay, so if I take 5 times 3, I get 15, 4 times 3, I get 12, and so on. It works, right? Okay, this one, this is the first time we've seen it. The 1/3 I can actually pull out. I can actually pull out a 1/3 because that's just a number. The constant can come out, and I've got 1 over n. Okay, I don't know if we've seen this before, except we wrote it at the very beginning. This is going to kind of come up more and more like this, where you'll pull out a number, and what do you know? You'll have 1 over n. This, let me see if I have it. Yep, it's the very first thing we wrote. It's the last thing we're going to use. Oh, this book is crazy. The harmonic series. The harmonic series, notice it's a series. Always, this is harmonic, so you want to write harmonic, and it always diverges. Harmonic series always diverges. When you have 1 over n, that's harmonic, and it always diverges. Okay. Now remember, if I wrote this as a sequence, we're talking a whole different story here. Okay. If I'm talking about it as a sequence, that's a whole different story. But if I'm talking about it as a series, this is always a harmonic series, and it always diverges. Okay, just looking at this, it would actually converge. But because we're talking about it as a series, because we're talking about adding everything up, that's a harmonic series, and it always diverges. Okay. Notice. Let's just talk about this. Do we have time? Yeah, let's talk. If you want to go to homework, that's fine. But what would happen if I did, okay, let's look at this. And I said, hey, I want to use the test for divergence. The test for divergence says, okay, I'm going to do the limit as n approaches infinity, and I'm just going to look at this guy, right? But what happens when this gets bigger and bigger and bigger? It's headed towards 0. And if it's 0, I can't make any conclusion. So it doesn't mean it diverges, it doesn't mean it converges. So this here, the test for divergence, just doesn't work. Test for divergence doesn't work. Okay. For this, because it equals 0, I just can't give an answer. But because it is harmonic, I know 100% that it diverges. Okay, so harmonic series is important. You want to look 1 over n. You want to remember that. All right, so you are doing now section 8.2, part 1 homework. Part 1, if you can see that homework. Okay, all right.